In this video, we'll be talking all about area under a curve and how to estimate that value using Riemann sums. So the region between a function and the x-axis is considered to be the area under a curve. And this region basically can be located above or below the x-axis. The area under a curve gives us what's called the accumulation of change. Let's think about a real-life example of accumulation and where we've maybe heard that term in everyday life. A common example is in terms of snowfall. So if we look at this example here, it says snow falls at a constant rate of 2 inches per hour over the course of 3 hours. How much total snow has fallen over those 3 hours? Well, we could probably reason this and say, okay, well, 2 inches fell over the first hour and 2 over the second hour and 2 over the third hour. So total, we're going to say that there are 6 inches of snowfall. That was our total accumulation. How much snow has accumulated over that time? But if we look at this in terms of a graph, if we take a look here, this graph shows the rate of snowfall in inches per hour and time in hours. So if I start to look at that region, we can see from 0 to 1, okay, the area of that region is 2, right? If we look at it, that's a rectangle. The base is 1, the height is 2, so area is 2. If we look from 1 to 2, okay, also 2. And then we're going to do it one more time. If we look over here from hour 2 to hour 3, another 2 inches. In total, that area gives us 6 inches. So again, we can look at this in terms of a graph, or sometimes when we have a real life example that's simple like this, we can sort of reason with it. However, that function was linear and it was a horizontal line, so we were able to easily find the area under the curve. Sometimes the area under a curve is not a shape that we can find the area of. In these cases, we have to use some approximation methods called Riemann sums, and there's 3 different types: a left Riemann sum, a right Riemann sum, or a midpoint, or we can use what's called the trapezoidal rule to estimate the area under the curve. Let's talk about how this relates to a bigger topic in calculus called integration. So we can estimate area using definite integrals. A definite integral gives us the area under a curve for a given function. So if we look at this here, A is basically our lower bound. So like in our example above, that would be like 0, right? That's when time started. B would be our upper bound. That would have been 3 in the previous example because we analyzed it from 0 to 3 hours. And basically a definite integral is equal to the limit of a Riemann sum as n approaches infinity. So you're going to see us go through on the next page of how to actually find the value of a Riemann sum, and we're going to be using area of rectangles to do that. And if you think about that, area of a rectangle is base times height, and that's basically what we're talking about over here. The f of x of k, that's basically the height, and change in x is going to give us our base, and that's going to give us our value of the definite integral once we evaluate that limit as n approaches infinity. So we're going to look at 4 types of estimation methods: a left Riemann sum, a right Riemann sum, a midpoint, and then also a trapezoidal rule. For each of them, I'm going to zoom out so we can see here, we're going to be using the same exact graph. We're just going to be coming up with our own estimates based on the given approximation method. So number 1 says use a left Riemann sum with 4 subintervals to estimate the definite integral from 0 to 4 of f of x dx. So what we're going to do is we're analyzing from 0 to 4. Okay, so again, this graph, we can see the x values go up to 5. We're only going to look from 0 to 4 because that's what our definite integral tells us. And when we start to draw some rectangles, and that's going to be our estimation method, we're going to start on the left because it asks us for a left Riemann sum. So if I look at the left of the graph, 0 is the leftmost point. I'm going to find that output, and I'm going to draw a rectangle going across, and then I'm going to drop that down. So we started at 0. The next leftmost point would be 1. Basically, where one rectangle ends, the next one starts. I'm going to find the output, go across, and drop down. From 2 to 3, find the leftmost output, go across 1 unit and drop down. And then the next output at 3, go across and then drop down. So if we take a look at this, here's why we knew to go over 1 unit before we basically dropped the rectangle going down. This problem asks us to have 4 subintervals. So if we're going from 0 to 4, that's how we can split it evenly so that we have 4 little sections. So from 0 to 1, 1 to 2, 2 to 3, and then 3 to 4. All right, so we're going to now find the area of each of those rectangles. So the area of the first rectangle would be 1 times 5. The area of the next one would be 1 times 8, 1 times 9, and 1 times 8 again. So we are adding all of these up, hence the word sum when we call them Riemann sum. And we can estimate that the area under the curve from 0 to 4 is 30 units squared. Let's try the same exact idea, same function, 4 subintervals, same bounds, except we're going to start on the right. So that means I'm not going to start drawing at x equals 0. I'm going to start at x equals 4. And I'm basically going to go across. Now I have to go backwards. I'm going towards the left. So if it's a right Riemann sum, you start on the right and then you draw your rectangles going to the left. I'm going to drop down. And then I'm going to continue to do that. And you're going to see here that some of these rectangles are above the curve, some of them are below the curve. That will change, and we'll talk about that in the upcoming lessons too, of whether the function is increasing or decreasing. That will change that idea. All right, so let's find the area. So the first rectangle is 1 times 8, 1 times 9, 1 times 8, and 1 times 5. So this estimate also comes out to be 30. All right, number 3. Use a midpoint Riemann sum with 2 subintervals to estimate from 0 to 4 of f of x dx. So we are now looking just for 2 subintervals. So if I'm going from 0 to 4, that means I'm going to have a rectangle that goes from 0 to 2 and then 2 to 4. So if I look at 0 to 2, the x value that's in the middle, hence midpoint, is 1. So I'm going to find f of 1, and that's where I'm going to draw basically the top side of my rectangle. And then from 2 to 4, 3 is in the middle, so I'm going to use that to draw my rectangle. And now we're going to find our area. So the area would be 2 times 8 plus 2 times 8, or 32. So remember again, Riemann sums are ways to estimate the area under the curve. You can tell that this is not exact because there's definitely some space above the curve that we are including, and there's some space below the curve that we're not including. So yes, we can get a good estimate through these methods, but eventually in later lessons in this unit, and if you're watching these videos through the playlist, you'll be able to see how to calculate the actual value of a definite integral. All right, the last one is what's called a trapezoidal sum. So in this case, we could basically take a guess here that we are going to be drawing trapezoids instead of rectangles. So just a note there, area of a rectangle was length times width or base times height. Area of a trapezoid is 1/2 the height times base 1 plus base 2. You could use some variation of that formula as well, and that would be okay. So I want 2 subintervals. So I'm going to do one from 0 to 2 and 2 to 4. So here's how we're going to draw it. We're going to find f of 0, f of 2, and we're going to connect them. That's basically going to be one of the legs of the trapezoid. If you remember from geometry, the bases of a trapezoid are parallel to one another. So when I drop down here, you can see almost as if you turn your head, the bases are really on the left and the right here. So they're not necessarily on top and bottom when you're looking at a trapezoid. Sometimes you have to just rotate it. All right, so now we're going to draw the trapezoid from 2 to 4. I already have f of 2 plotted, so I'm going to plot f of 4, and then I'm going to connect those. And you can see how I have two trapezoids. So the leftmost trapezoid is 1/2 times 2 times 5 plus 9 for our base 1 plus base 2. We're going to add that to the area of the second trapezoid, so 1/2, 2. And then it's going to be our same numbers, 5 and 9, or 9 plus 5, either way is fine. And we can estimate our area is 28. So those are the 4 types of estimation methods. So a left Riemann sum, right Riemann sum, a midpoint Riemann sum, and then a trapezoidal sum. Just a couple of questions to kind of recap these approximation methods. It says, consider each type of function and decide if the method of summation will be an overestimate or an underestimate. So A says an increasing function using a left Riemann sum. So what you could do is you could draw just a picture of any increasing function. So let's say I just draw a line. And I start drawing boxes going from the left. You can see as I go across that my rectangles are under the line or under the curve if you drew a curve. So we would say that this is an underestimate. Let's say I try B. It says an increasing function. So I'm going to draw the same exact one, but a right Riemann sum. And we could probably guess that this is going to be the opposite. You can see that I'm over the line or the curve that you might have drawn. So this would be an overestimate. We could verify that by our graphs above too. If we take a look, if we find where a function was increasing and we used a left Riemann sum. So if I look at number 1, here's where the function is increasing. The rectangles are below the curve, so that would be underestimate. Whereas if I look for where it's increasing and it's a right Riemann sum, look over at number 2, the rectangles are above the curve, therefore overestimate. And then for C, a concave up function. So let's say that I draw something that looks like this. It's got to be somewhat of an upward U shape. And I start drawing trapezoidal sums. You can see that this looks pretty accurate to my actual drawing here, but a concave up function using trapezoidal sums will be an overestimate.